Alright, we're going to get started in SPSS. We're going to follow an example by Humax and Haswald from our Statistical Concepts textbook. So this is just the same data that they use as their one-factor analysis of variance for fixed effects models. I'm just going to walk you through this so that you have a little bit of extra help. We'll do some of this in class, but this is just an extension. But again, not meant to be as many of our videos are. It's not meant to be just a standalone tool, but just helpful as you go through and work through some of the examples and homework assignments. So here we have our data set for Stats Lab open. We have the variable, our independent variable, which is labeled group. And then we have labs, and as we went through in class, in our mini example, we saw that there were levels of attractiveness. We did a subset of this data, but we can check here under the variable view. Again, some of this data view, variable view should be review. If it's not, please see previous videos and come see me during office hours. So group has 4 different values. We have group 1, 2, 3, and 4 from unattractive to very attractive. And then our outcome is our dependent variable, which is labeled labs in the variable view, and our data view we see it here. So that's just a quick through for that. Basics of our data. So let's get started. Analysis of variance. Our very first SPSS analysis of variance, well, full. Maybe it's our second analysis of variance. So let's go through, and we're going to go to Analyze, General Linear Model, Univariate, and we'll select Univariate. We have our dependent variable, which we know to be number of stats classes attended. We're going to put that in as our dependent variable. Our level of attractiveness is our independent variable, and its fixed factors. Those are pre-selected. We will be talking more about random factors and repeated measures later on in the semester. But for now, our one-way fixed factor, or one-factor analysis of variance, we're going to put this in as a fixed factor. So now we have our basic analysis set up. And we'll see a couple of our options and plotting here as well. So let's go ahead and go to Options. And under Options, I always select Descriptive Statistics, Estimates of Effect, and Observed Power. We'll also go ahead and select Homogeneity Test. We can see that we could select display means for specific variables. So I'll go ahead and put our factors overall and group into this box as well. We'll leave here. You see significance level 0.05 and our confidence intervals are 95%. We'll leave those as their default. We're testing at 0.05 level and 95% confidence intervals being produced. I'll go ahead and select continue. Next, we will go ahead over and we should probably do some plots. We'll simply use the groups. We kind of want to see from groups 1, 2, 3, and 4 the difference on the means. So if you go to groups, add them to the horizontal axis as I've done, select add, then you can go ahead and hit continue. We'll get some plots that will produce basic mean plots for us that we could graph ourselves, but instead SPSS will do it for us. In class, our assignment, we did a little bit of self-graphing, and here SPSS will be assistance to us. Finally, let's go ahead and hit save. I'm going to hit unstandardized residuals. Some of you may actually get this data set with these already, but if you haven't, you'll be able to produce our residuals, basically our deviation scores, and we'll just save those for now. I'm going to go ahead and hit continue, and then I'm going to select OK. If all goes well and seems to have gone well, we should be both modeling. You should be seeing when you practice what I have here, and also this should be modeling again from our course textbook. We should be producing the same results. We have outcome measure. Our first thing that we can look at is for each one of our value labels. We have groups 1 through 4. We had 8 people. That is correct. That's just a double check. We'll see later on in the semester that we will have situations where we may have different number of people in each group, but for now we have balanced groups. Our descriptive statistics is just the basics, and we'll see these means plotted later on, but we can see that we have both mean, standard deviations, and n for each one. You could go back and either calculate these by hand or later on go back and do an analyze and check the descriptives for another process, but you'll get the same thing. Now, we have our first test, which is Levine's test. And hopefully you recall or have been doing some review of your introductory stats course that this is another F-test, and Levine's test is whether or not we can assume that variances are equivalent. So if we were significant, 0.05, we may have some issue with equivalency of our variances, but in this case it's 0.45, which is well above 0.05. So we don't have to be concerned that we violated the assumption of equal variances. Also, as an eyeball check, when you go to your descriptives, see that I'll highlight them now. Your standard deviations, obviously if you squared those would be your variances. Those are all relatively close to each other. So even just descriptively, we can see that there's some approximation that our standard deviations or variances are equivalent. All right. I'll extend this a little bit. There we go. Now to the heart of our test. We did these by hand in our previous class, and now we're going to take a look at what comes out of SPSS. I could quickly show you a couple of the critical elements. We have significance, and we have our F. Notice that the corrected model F value and the group F value, are both 6.8 with a significance of 0.001. This will be the case for our one-way analysis of variance. But we're really interested, even though they're the same, we're really interested in that group F value. That is the effect of our between group variance. So we can see that if we were to go back, and you might want to practice these calculations, and we'll do so in class, that mean squares between 246 divided by the mean squares error or within of 36, that's this column right here, 246 and 36, that ratio is 6.8. And we saw in class where we did mean squares between over mean squares within. Here, SPSS is calling that mean squares within error. So that's how we could calculate that. We have 0.001. So we have a significant F-test. Note that we have our degrees of freedom are 3. Remember, K minus 1 or J minus 1, number of groups minus 1 for our degrees of freedom for between group. We see that we have 3. And for our error, recall that we have the number of people, we have 8 in each group, times 4 is 32, minus 4 for the number of groups, that gives us our degrees of freedom error, degrees of freedom for within groups. Alright, we also notice an effect, well, I should say we have both a partial eta squared, and we actually have r squared as well. Partial eta squared and r squared in this case are the same. We'll go over in our class how to calculate those, but basically we're taking the mean squares between over the total for our eta squared. And for partial eta squared, we'll sort of take our between plus our error in our denominator and separate out that total. But this will be a little bit different when we get to more complex analysis of variance. But for now, our partial eta squared is our effect, as well as we see that that is also in our r squared. So we'll calculate these, but effectively 42%, we can say, that 0.42 is like saying 42% of the variation in the dependent variable is accounted for by our independent variable, in this case, the attractiveness of an instructor. So we also can see that we have power at the very end here, 0.95. I like to say power is our chance to find significance if it should really exist. So it tells us whether or not we had a powerful enough test to find something. Most of the time, if you found significance, you usually have relatively high power. We want a kind of a minimum of zero point 0.8 or above. This should already recap. So we have a 95% chance of finding a difference if there really is a difference, or really is a chance of rejecting the null hypothesis. And I think that's enough on this chart for now, but as you come back and you practice, you could easily go through and take your sums of squares appropriately, divide by degrees of freedom to calculate your mean squares, to calculate your F. This would be great practice and practice to understanding where the within and the between groups mean squares and sums of squares are coming from. In class, we talked about the gram mean and the mean for each group. We have the gram mean calculated for us. That's the mean across, if we were to not count any group differences, the mean across everyone, the average across regardless of group, or kind of the average of averages. We also talked about thinking of it like that, as well as a 95% confidence interval around that mean, that gram mean. Level of attractiveness, these should be a little bit of a repeat. I'll just kind of pull back up a little, and we can see that for our descriptive statistics. Unattractiveness, the mean was 11, slight attractive 17, 20, and 24. We also see that that average of the average there is 18.4. Well, that's 18.4 for our gram mean we see here. And we see those mean values are replicated. As well as we got a nice confidence interval. One of the things I love about confidence intervals around a mean, maybe love is a little bit too passionate of a word. One of the useful things that I find with confidence intervals around my mean is that I can see that 95% bound around that mean of 11 is 6.7 to 15.4, and I can see some of the other mean values don't fall within there, which starts to tell me some of what we'll learn when we get into our looking at group differences and multiple comparison procedures. That starts to tell me that the mean of one group doesn't fall into the confidence interval of another. There's probably a difference here, and that's where the differences lie. And finally, I went ahead and did the estimates. These are our plotted estimate marginal means. So this just gives us a high-level view of the differences kind of plotted together. So I'm going to stop this here, and I'll come back for some of the other tests that we might be able to do, as well as testing some of our assumptions in a separate video, just so if you want to go back and listen to this, you don't have to hear the entire video at once. And also I'll try and do this throughout the semester, and also so that you can be focused on what our basic concepts for each video. And in here, the basic you should be taking away is being able to conduct and interpret the analysis of variance, as well as some of the effect size and power